Thank you. So welcome everybody to the colloquium today, and our speaker is Marianna Safronova. She got her undergraduate degree in Moscow State University. She then came to US and got her PhD in Notre Dame, and then very quickly after one postdoc she got a faculty position, and you will see that during that time her interests became so broad that it's hard to imagine that they could be that broad, but it's all contained in one person. And with that, we're welcoming Marianna.
Thank you so much. Should we make it? Could you see better?
This is better.
Okay. So as you see, the title of my talk is the title for the whole course. And since we only have like less than an hour, we are going to focus this on how to listen to invisible, puzzling universe with quantum clocks. So what you see here, you actually see individual atoms. So every those little ball, it's literally an atom which is held by light in an artificial light crystal. And then you can manipulate those atoms by lasers, and that actually builds the most precise devices in the world to measure anything. Because the frequency, it's one quantity which you can measure better than anything else. Our story starts 100 years ago. Okay, raise your hand if I know what those pictures are. Yes, it's a code. It's a universe puzzle. So when people started measuring those atomic spectrums, they found out that atoms do not absorb or emit light of any frequency. They absorb and emit light of very specific frequencies. And the main question is, why? So by 1926, people knew why those things were in those discrete lines. It's because atomic energy levels are quantized. This was the birth of quantum mechanics. What they still didn't know is why those lines are in those places and why there are that many lines. And that was literally a cipher which one had to crack. And not only the quantum mechanics was born to explain this, quantum field theory was born to explain this, because some of those lines split just a little bit because of the quantum electrodynamics effects. And it took till 1940s to actually explain this. So my background is atomic theory, so I can actually compute where those lines should be. And most importantly, the quantum mechanics, it's a golden standard for theory. Not only we understand this, you can give me an atom which people never measure, like nickel 12 plus, my experimental collaborators want to build the flux from, or californium 15 plus, believe it or not. And we can predict where those lines will be. So, and that level of understanding of quantum, that would give rise to quantum devices. So despite the fact that that was a completely fundamental puzzles, this is the reason why we have lasers, why we have computers, why we have those wonderful quantum technologies. And all of those devices only really required understanding and harnessing this power of quantum. However, the next quest was how to control quantum. How you can take an individual atom, cool it to the point that it's literally motionless. And now, if it's motionless, you can actually put it in a trap. And those traps depend whether you take a neutral atom or you take an ion, which is charged. And then, because it's so cold, you can put it exactly where you want it and keep it there for a long time. And now, since you exactly know where it is, you can precisely control it by lasers. And precisely control, you can engineer its state. And by the way, people kept ions in those traps for years. They named those as pets. So literally, some of those traps could be very, very long-lived. So the quantum sensors, it's devices with engineered quantum states. So because you can cool, trap, and control, that not only gives you ability maybe eventually to build quantum computers you may be heard of, those are exactly the same type of technologies people are using for quantum computing. So those devices allow you to measure frequency and therefore time and distance, electric fields, magnetic fields, gravitational fields, to really exquisite precision. And that's what I mean by quantum sensors. So if you need quantum mechanics to describe the device, we call it quantum. If you engineer its quantum state and manipulate them to read out your property, that's what I call quantum sensors. So superposition and engineering quantum states required, entanglement is not. And now, 100 years later, after the understanding of puzzles of atoms, we have the whole array of what I call quantum sensor. And I literally just put it there so you knew that there is this whole large field besides atomic clocks, which I'll talk about. You also have atom magnetometers, which measure magnetic fields, which is exquisite precision. You can have atom interferometers, which can literally measure the gravitational potential. They can be used for many, many different things. Those are measure phase difference between different paths. You can hold nanoparticles by light, and you can also have many different experiments with trapped ions, molecules, and other quantum devices. So I will talk about atomic clocks, and the reason why is because atomic clocks are most precise devices ever built to measure anything. So you can say how precise. Those clocks will not lose 1 second in the lifetime of the universe. And since these are two large numbers, lifetime of the universe, let's make another example. When they first got to the point of 17 significant figures in those clocks, they, of course, started building more of them. So at NIST, they had 2 clocks built from exactly the same atom, exactly the same frequency. They just were on the same floor in different labs. And they didn't quite agree. So they ticked at a little bit different rates. Because you can connect those two things to the same measurement device, a frequency comb, and you can determine whether the frequency is a little bit different. So it was the same clocks. They were built the same way. So why? One clock was on a table which was a foot higher than the other. So the clock at 10 to the minus 17 levels can measure differences of 10 centimeters. Actually, it was like less than a foot. They, at that point, have 3 times the The most modern clock can measure a difference of 1 millimeter. So it's literally a geodesic device. So you can not only now measure time and frequency, you can actually read the gravitational potential. You can literally look at real times. If you put it on a glacier, you can determine the height of the measurement. People would like to put those to space to measure properties of actual general relativity to test this. So that's why clocks, because those are the fantastically precise devices. And by the way, yes?
Ma'am, I could put a marble on a table that's off by a few millimeters, it will roll down.
You can integrate in real time, and there's no classical geodesic device which can do that.
Okay. What I was saying that there's something that detects 10 centimeter difference is not that big a deal.
Something which can tell you where you here and another person a while away is at the same height. It cannot be done any other way more precisely than clocks. So let's just get.
So what's the sensitivity? I mean, I somehow cannot compute in real time today. So the sensitivity of 10 centimeters, what's the difference in gravitational potential?
So frequency in what units? It's literally, is that literally measuring a millimeter in height?
No, but I'm saying that let's say that you have like a whale, right? I mean, if the whale sits by your clock,
okay.
at which
not
point
the whale, but if you have, let's say you have a volcano, and you have a magma chamber kilometer by kilometer. At 10 to the minus 18, you can tell this if it's filled. You can do it with other atomic devices like atom interferometers as well. So this is particularly sensitive to height, actually. specifically. So people in Japan would actually see the ocean around Japan with microscopic clocks and literally see how the Earth's floor, like sea floor, changes with height. So this is one of the applications.
Excuse me, which clock technology achieves the 10 to the minus 17?
So 10 to the, like the one which I mentioned in 2007, that was aluminum plus. But now the most precise are strontium, terbium plus, then lutetium plus, and aluminum plus. So there are several of them.
The old technology was cesium. What resolution does
Cesium
it
is
get?
100 times worse.
Thank you.
Yes.
What about motion of like core of planet? Does it change? Because I assume like since there is so much ground below us and there is
It
fluctuation.
is common. You measure the differential. That would generally be common to both clocks. If something happens inside, as I said, volcano, rising floor, magma chambers, that's kind of application. Something deep inside Earth we can't tell.
But I feel like distribution of mass would change, so potentially.
Yes, but it will be very difficult to attribute it to something which is not normal. But it's an interesting question, maybe in the future. Like in the future, we really hope that we could see evolution of the wave function that curves space-time with clocks, but we are not quite there. Okay, so now let's talk about new puzzles. Before puzzles, this is what we know about physics in a very elementary kind of condensed sort of way. We have list of particles. We, meaning many colleagues over time, found those particles. We have now discovered the Higgs boson. And then we have quantum mechanics and general relativity. Of course, our problem is we know this picture is woefully incomplete because we don't know what universe is made of. It is not made out of the standard model. So only 4% of the universe appears to be made from stuff we know. And this is our new nature puzzle now giving that 100 years. So we start with puzzles of 1926, and as a result we got quantum mechanics. Now we have totally new puzzles, dark matter, dark energy, many others which I will not talk about, antimatter asymmetry, for example, for which you study CP violation. That's a whole different talk. And now we have new technologies because we solved the other puzzles, and we would like to use this in extraordinary precision of the clocks to now try to actually find dark matter. So I will talk about dark matter first, introduction to dark matter, how one could search for it, why we could search it for clocks. I will give a bit introduction to clocks, and then how to actually search for dark matter with clocks, and then I'll talk a little bit about how we are going to do it in space. So why search for dark matter? Well, for the same reason you would climb Everest, because it's there.
Or you think it is there.
Good point. So why do we think that it's there? Well, because frankly we don't have any better idea. So it's not as theory as a quantum mechanics with predictive quality, but it's kind of rank 2, we all agree that it is kind of so. Yes, there could be modification of gravity. So far no one came up with actual modified theory of gravity which explains all of this. So there are many evidence for dark matter, and one of them you may have heard is that velocity of stars in a galaxy does not fall off as velocities of the planets in the solar system, and it actually remains flat. And really one of the only ways you can do it, you can put way more matter in a galaxy way outside of our galactic disk. This also is confirmed at different scale of the whole galactic cluster. So those two things is called bullet cluster. And like there's literally many stars and many galaxies together. And what happened is that one galactic cluster is passed through another galactic cluster. Okay, what happened to stars? Nothing. Well, maybe a couple of them collided, but probability is very low. What happened to dark matter? Nothing much, because it's very weakly interacting with itself. However, the hot gas, which permeates those galactic clusters, has friction. So what are you seeing here? In blue, it's what we are seeing in gravitational lensing, where the matter is, whether it's dark matter or normal matter. What you're seeing as red it's hot gas. So you see it's displaced to actually more than 10 sigma from the where the seeing the matter. And as you see, it also has this bullet shape because the gas, one cluster passed through another, therefore compressing the part of the gas and dispersing the other part of the gas. And there are many of those clusters, I think there are more than 30, and this is one of the has many standard deviation that those center of masses actually offset. As of now, there is no known way modifying gravity to explain this, or actually any other way, except the fact there's a huge invisible dark matter, which makes the center of mass here. Because the hot gas, there is way more hot gas than stars in terms of mass. But the main reason why we think dark matter exists is because we exist. It's because galaxies exist. Because if you start at cosmic microwave background radiation, which is a remnant of time in the universe 400,000 years after the Big Bang, when atoms finally cooled down enough to actually form. So at this point, hydrogen formed. And that allowed light to propagate freely. Because before that, if you have charged particles, your light keeps scattering. And when you have neutral atoms, hydrogen cannot absorb light at the time, except at very specific frequencies. So if you propagate this in time, you see those overdensities. Those are those red and blue spots are how the matter was distributed at that time. And it's very even. So distributions of matter only differed by 10 to the minus 5. So if you see how they propagates in time, the redshift was 1100, it more or less distributes linearly. So propagating in time, multiply 1100, 10 to the minus 5, we should not have galaxies by now. So without dark matter, it's not possible to form large-scale structures of the galaxies which are now observed. So it's not possible for us to be here without dark matter or some other alternative explanations, which right now we did not come up with. That's
So
why
today, delta rho over rho is bigger or smaller? Today?
Well, the overdensities are huge because we have huge
Okay,
voids in
alright.
galaxies.
So
of
it
course.
is bigger.
Increased.
So could it be some sort of particle? So here's our standard model. Nope. And technically, neutrinos could be considered dark. They're not interacting electromagnetically, but they're too hot because they are relativistic at CMB. So they cannot be significant fraction of our dark matter. Therefore, you need to search for new particles. All right, let's do that. Let's say we have some new particle, which is dark matter. Yes.
Primordial black holes?
Primordial black holes cannot be 100% dark matter because that's been ruled out. Also, they could be significant component, but my understanding is you need to make them cluster in a weird way for it to be 100% dark matter. However, people are actively searching for them. And the reason why we're talking again about primordial black holes is because LIGO have seen really large black holes. On the other hand, it's really easier for LIGO to see large black holes. So, but yes. Now, there is a whole other graph which puts primordial black holes another sort of what we call composite objects which are not a single particle. And yes, they could be like antiquark nuggets, possibly. But if it's just a simplest theory of one particle, unfortunately, we have many orders of magnitude limits, because on that part, eventually, dark matter has to bind the smallest known galaxies, and it puts limit as somewhere in between 10 to the minus 22 and 10 to the minus 19 electron volts. On this point, eventually, at Planck mass, your particle becomes a black hole, and we are back to primordial black hole scenario. A lot of orders of magnitude in there, about 60 or so. And frankly, we have no clue of what dark matter mass is, or for that matter, its interactions. So WIMPs have been a fantastic, and still are, a fantastic candidate, something about JV, and I actually will show you how people search for them.
One question.
Yes.
You said a moment ago that dark matter was very weakly, if at all, self-interacting. So it appears we do know something about it.
Okay, very weakly interacting we know because we assume that during the bullet cluster it didn't interact with itself more than once. However, that is at velocities of the bullet cluster. So we know something, we just don't know what it is. So mostly we know what it doesn't do. but we don't know what it does do. We know that it interacts gravitationally. We don't know if it interacts in any other way with a normal matter. However, you have to produce it somehow. It's possible to produce it gravitationally at inflation, but difficult. So, which leaves us hope that at some point it did interact with normal matter to be produced. All right, so how to look for particle dark matter? Let me tell you a story. During COVID, maybe some of us found new hobbies. I found the hobby of photographing birds. Okay, so I got the camera. If you go to the forest trying to find a bird, your cross-section with a bird in the winter is not very big. They tend to hide also. So I went back home, I put food out for them, I had a nice bird feeders, and the birds came. So, and sometimes I didn't see birds, but I just seen seeds and other stuff disappear. So, and I just sat there with a camera and waited for birds. That's pretty much how we look for particle dark matter. So,
What's the seed?
we build a trap. Okay, we don't attract dark matter. We just make cross-section with dark matter more likely. So we find somehow a material, and we put a lot of this material, frankly, we do put underground, and we just wait for dark matter to come. Okay, we can't trap it because it's really not interacting much with anything, so mostly it'll just scatter and go away, but it does deposit energy. So it could deposit light, heat, or charge. Because, well, it's scattered, so you have some heavy thing which just scattered off your nucleon in your material. And let's say material germanium, and therefore, as a result, you will get photons, you also get charge. Usually, out of light, charge, and heat, we would like our detector to actually get two of them for purposes of cross-checking. Those, unfortunately, are also be affected by cosmic rays. So all those detectors usually sit 2 miles underground. By the way, we are running out of space at 2 miles underground. One of the biggest problems in the US is that they actually need to dig a very big hole underground to put further detectors in. Unfortunately, this works if your particle is heavy. If your particle is not weighting the size of the nuclei, you can try different things, but eventually by about electron volt, no material will give you a deposit of sufficient energy for you to detect the particle. More than that, you end up with lots of particles per de Broglie volume. So at a certain point, you no longer can detect matter particle by particle. So at under about 10 electron volt, your dark matter becomes behaving like a wave. Why? Because, well, you have very, very large occupational number, like say 10 to the 30 per de Broglie volume at 10 to the minus 6 electron volt. Therefore, for all purposes, it's just cosine plane wave. And it does have a property. There is a dark matter field amplitude. This is dark matter density, which we know it about 50%. Even though we don't know exactly what it is in the solar system, we do know on average what it is in our galaxy, for our galaxy to be the way it is. And then dark matter mass. Notice that dark matter mass directly connects to its frequency of oscillation of those waves. So now, our dark matter is coherent on the scale of detectors or network of detectors. None of the particle detectors can detect this. So now, that's why we would like to have quantum sensors. So what will such dark matter do? Even if we don't know what it is, if it's spin 0 or 1 particle, we know how it has to couple to standard model. And we know which effects it will cause. It can precess any spin. It can produce currents in electromagnetic system. If you heard about axions, axions can be converted to photons in magnetic fields and vice versa. Now, scalar dark matter, which I'll talk about, will actually change fundamental constants. Yes, those constants in the back of your physics book, like a fine structure constant, will actually oscillate. Therefore, every atomic energy molecular level will oscillate. Therefore, the clock frequency will oscillate, and you can measure this. So, more than that, different clocks will have, because different energy will have different sensitivities to this effect. So we can measure the ratio of two clock frequencies and then monitor it over time. So our observable will be measuring of two clock ratio. For any particular physics in there, I thought I need one page with Lagrangian. So this is my one page with Lagrangian. So this is so-called diatonic coupling. You may notice this is your F menu electromagnetic tensor we all know and love from Jackson E&M. And this is your new scalar field. And what you did, you just multiplied every term in a standard model Lagrangian by oscillating field. Therefore, you redetermine every single coupling and every single mass. And yes, electron and proton mass will oscillate. The radius of the nucleus will oscillate, and any energy level will oscillate. And there are different ways to look for it. And your key point that you have different types of clocks are sensitive to different effects, and your observable is clock frequency ratio. So you take two clocks, measure the ratio of two clock frequency. Good news, that's what metrology people do for a living. They have to actually measure the ratios of clock frequencies, and there are years and decades of those measurements. Of course, we can do it better, but we already actually have recorded data. And then we keep measuring many graduate students sitting in a lab for duration of the grant, the staff position, lifetime of the universe. And then you look how this ratio changes with space and time. Yes?
Can you measure the presence of neutrino, for example? Like if dark matter has similar
Not
mass
yet.
as neutrino?
Unfortunately, okay. No cosmic rays doesn't do, or neutrinos or anything doesn't do anything to clocks because they all interact with this too fast. And neutrinos, we are not sensitive to that at all. Like the muon will not do anything to my clock because it passes about picoseconds, and 5 floors of concrete kills most of the muons for all purposes. I can't. So no neutrinos.
How fast is the dark matter?
Aha, because this is different dark matter. We are not neutrinos. You are still searching particle by particle. Here, this is a completely different way to look for. That's why we can't look for neutrino. We can look for ultralight scalars, which are much lighter than neutrino. Just because they couple differently to my atoms than neutrino does. Question?
Why is your couple proportional to 1 over Planck mass and not some other scale?
Because my particle physics colleagues know that we haven't found it yet, and they need to divide everything by some very large number.
I know, but you know, why by Planck scale? I mean, it's a bit,
Well, because you can do it at a different scale. The Planck scale seems like a good idea. That's unfortunately the only. This is also the reason why they cannot tell us when we are going to start seeing dark matter, even though we know the density, because we have no idea. Look, frankly, that makes absolutely no shred of difference, because that Planck's mass, it's going to couple into the unknown quantity dE, and this is just a nice to normalize it. Because particle physics colleagues do not want any coupling which is 1 over the Planck's mass or below. So it's kind of a nice way. If it's 1, that's a kind of gravity level. So d of 1 will mean something in that particular type of field. It doesn't have to be more than 1.
Well, my point is that usually when you write an effective interaction like that, the scale that you put in the denominator is the scale at which your effective description breaks down. I know for sure that none of that would be correct at Planck scale. Right?
Look, all it is normalization of those couplings, because those couplings are known.
Okay.
So, and this is also people use different things. This is kind of generally what's been accepted in the literature. So, yes.
I don't see the axion there coupled to the dual.
Because this is scalar. This is scalar couple. Pseudo-scalar will not couple this way. It will sort of couple this way if it's somewhat not fully. It action could have some diatonic coupling if it's not perfect QCD action. But right now, this is kind of an exotic thing for us. So technically, we could use this to search for axion, but this is slightly exotic. So axion will just have different Lagrangian with different types of couplings. Questions from students? Yes.
I just wanted to make sure that I'm follow you, because the way you detect is we compare to exactly the same clock, and it is
No, I would like to different clocks.
different clock.
So the reason why it have to be different, because let's say, so each clock, for each clock I can compute how sensitive this to variation of fine structure constant. I literally just change fine structure constant in my code and it tells me this energy level has sensitivity of 1, or this level has sensitivity of 10. And this is a relativistic effect. It's literally a number which has to be computed.
Then how does it connect it to
Okay.
dark matter?
So, because the reason we are sensitive to dark matter here, it's because dark matter modulate value of fine structure constant. So alpha is this fine structure constant, which is normally 1 divided by 139. Okay. Now, right now, this is 1 divided by 139 multiplied by some sort of cosine oscillating field. However, there is an additional coefficient of how do I transform, this is my energy level, and this is sensitivity to this effect. There is an additional atomic physics calculation which comes in there. So there is accuracy of the clock, and then there is sensitivity to dark matter. Because the more relativistic my atom is, the heavier my atom is, the more it has alpha square plus something, somewhere inside its structure. So it's meaning that the more, so alpha squared is a relativistic effect. So the heavier the atom, the more sensitive it is to the thing, just because it depends more on alpha. The more it depends on alpha, the more sensitive it is to variation of alpha, the more sensitive it is to dark matter. But then I need to measure relative to something. So let's take aluminum plus clock, which is very light and has very small sensitivity. And as you know, in any, like in hydrogen, you have alpha square in all the energy level. This is on top of this.
So we're build a device clock really sensitive to dark matter.
Yes. So unfortunately, most of our clocks are not very sensitive because the clocks were built for completely other purposes. So I will tell about specific clock which you want to know. So, but mostly what's already in a lab, they have sensitivities between 0 and 6. 6 because it's heavy, ytterbium plus it's heavy, it has very special shell which sits closer to the nuclei, it's relativistic. So generally, that's why we would like to measure the ratio of two clock frequencies. One which is not sensitive, one is sensitive, or one which has negative sensitivity and one which has positive. It can actually be both sides.
So the sensitive is proportional to something like a distribution of dark matter?
No, sensitivity is just proportional to it's a property of particular electronic transition and how sensitive this electronic transition to alpha variation. Like look, a hydrogen atom would have a constant in there which is Rydberg constant, right? It has alpha square in it. So every atom therefore will have proportionality as alpha squared. But if it's the same for all atoms, it will cancel out. Therefore, we would like to find the one which has some additional sensitivity just due to its electronic structure. I'm happy to discuss more after the talk. So, important point, there is sensitivity which we can compute and which we understand in atoms very well. Therefore, we build two clocks with different sensitivities, and just we keep measuring this ratio, and then we extract variations which are due to this dark matter. There are different ways to do it. So the question is, when I say dark matter oscillates, the question is at which frequency it oscillates. So for clocks, characteristic frequency on which you can measure, it's a hertz. Well, because look, if I do measurement every second, it means I am sensitive to something which oscillates at 1 hertz. And making measurement every second with a clock is all right, a couple of parameters. So 1 hertz, it's about 4 × 10⁻15 electron volt. So we are looking for actually frequency which corresponds to wavelengths the size of the solar system, or like significant part of the galaxy. So we are looking for very long wavelengths. So we are actually way beyond the radio. Some of the people who look for axions, they literally kind of call, there is one called DM radio, which is literally like gigahertz type stuff. We are actually way more in the hertz region, but we can say that what we're actually doing now, we are literally listening for dark matter with our atomic clocks. So we have the waves of dark matter which permeates everything, and they affect our clocks, and we're looking at the clock frequency ratios. Right? So now, what is atomic clock? If anyone ever see a pendulum clock has a period of half a second. So its tick rate is very slow. What we would like an oscillator which ticks very, very fast. And that's what atom does. So atomic transition between, say, ground state and some excited state can oscillate with a frequency which, in this case, if you take atomic clocks of an optical spectrum, so you have something like 400 nanometers, so it will be oscillating at about 10 to the 15 hertz. So atoms are all the same, so those are perfect oscillators. So we'll take sample of atoms from one, and we'll build a device which therefore can excite this atom directly on resonance. This means laser. If you mentioned cesium before, those will be lasers, those are microwaves. Here we're actually exciting them with a laser. And then we count the cycles of the signal with another laser. So the basic idea is a clock as a tuning device. So we have a standard of frequency, that's my atomic transition, and we have ultra-stable laser, which can work for a little bit without the clock, and then we tune it to be on perfect resonance. So as you can imagine, that involves fairly complicated service system. So now, here's my laser. I'm trying to excite my atoms. Atoms did not quite excite to the excited state, so we are not close to resonance. Tune my laser again. And now, finally, my atoms are saying, yep, I got excited. And you measure actually population of atoms there. And then that allows you to scan through this entire frequency reference, and then you count it with a different laser called the optical frequency count. An important point that, as you remember, 1 second is defined by cesium. So cesium is 100 times worse than those clocks. So we cannot actually measure the frequency directly, but we can compare two frequencies to much, much better than a cesium standard using those frequency counts. Questions?
How
Yes.
precise tuning of this laser do you need? I assume which affects accuracy of time measurement?
This frequency comes and can be tuned essentially to like liter near exact resonance. You can tune them wherever you want. So the steps, so you get 18 figures. So you're actually better than a millihertz in terms of measuring frequencies. So this is actually, as I said, fantastically precise. So what steps experimentally usually use? Okay, I'm a theorist. Other questions, especially from students? Right? So how do you know how precise your clock is? As you can imagine, you have a lot of problems with the environment. So what happens to your clock if your lab temperature rises? Or if there is a magnetic field in the other lab? Or if students walk in the room, do you care? In terms of gravity, okay, whale, as we said, doesn't matter, the mountain does. So what experimentalists do, they actually think about all possible things which can affect the clock frequency, and then they quantify them, they add them in quadrature, and that's how they get total clock uncertainty. And this takes years to do. For every new clock device, they have to quantify them. They also take those clocks and compare it to each other and see if the ratio of the frequency actually is precise to the square root of those uncertainties. So this is actually a very complicated procedure, and people have thought for a lot of different those systematic steps.
Can you describe the BBR?
Yes, I'm glad you asked. So this is black body radiation shift, and this happens just because the clock is at 300 Kelvin. And it's literally a black body shift. So everything which is in some sort of ambient temperature would therefore will result in a frequency dependence. This is actually a large effect. This is about 10 to the minus 15 effect. So that's why it has to be characterized with exquisite precision. And I, as theorists, actually collaborated on this paper to really get the numbers for black body shift. All right, in principle, you can put this whole thing in the cryogenic device. And the temperature dependence is T to the 4th as the primary dependence. There is additional T to the 8th dependence. It's very important, if you do cryogenics, it has to be an extremely even cryogenics. So whatever's inside, therefore your vacuum chamber, has to still be at a perfectly very cold temperature. Now, if you get to the point of 4 Kelvin cryogenic shield, black body shift is 0, literally. So, however, people really do not like cryogenic devices in precision labs. So they try to avoid it as much as possible, especially since now we are making those devices portable. I know the Riken clock actually works at 200 Kelvin, and they were able to reduce it just doing this without cryogenics. So this is kind of eventually next step, but people really try not to do it. Now, people who build clocks from highly charged ions just because they always work with cryogenics, not understanding the problem with other people. So they said, yeah, just cool it down, and that goes well. As you see, this is the largest shift. So cryogenic, there are several cryogenic clocks which already exist. The other thing is the fact that you're actually shining light into the atoms to actually make those traps. And those traps have electric dipole component, then magnetic dipole, electric quadrupoles, there is a hyperpolarizability. That's where the next comes from. So it can be controlled though. So, but this is really an exquisite work to get this all working. So, optical clocks will continue to improve. There is no technical limit for many orders of magnitude, so we are like right there right now. How far down this rabbit hole goes depends on the level of optimism of experimental colleagues you're talking to. So, but there is no reason why we cannot go very, very far. We also eventually would like to be able to measure beyond the quantum limit. And by the way, this is cesium. So the cesium actually ended here. It is not going to get better. And this is almost kind of Moore's law here. So also you can make very large ion crystals. The more ions you have, the better your statistics is. And eventually you can actually entangle particles and work with entangled clocks. So there's very, very many different things you can do to improve. But of course, the important point, we would like to have as much sensitivity to this alpha variation or other constants as possible to get our dark matter search as good as possible. Therefore, can't we build different clocks which have much, much higher sensitivity limits? And the obvious question is, can we build clock based on nuclear transition rather than atomic transitions? Because those are much higher frequency. So this is where we're at right now. So this is an awful plot because it puts many, many experiments together. So what it does, this is a mass of dark matter, and this is this coupling d, the one which is divided by the Planck's scale to the Planck's mass. So as you see, the coupling of 1 would be somewhere right here. So we are actually well below those limits. And there is this whole issue of the axion quality problems and so on. My particle physics colleagues can tell you how to get rid of it. So if you have some symmetries, you can actually get rid of that. So here is current clock limit. So everything which is shaded, that's where we're at right now. The nuclear clock, that's where we can get if we actually build clock based on nuclei. A very specific, very special nuclei. So a question to you, why is it such a problem to build a clock based on nuclei? So what is different about nuclear energy levels comparing to atomic energy levels?
Separation.
What?
Separation.
Yes. Usually nuclear energy levels are something like mega electron volt to kilo electron volts. And even I'm not optimistic that I will see mega electron volt tabletop ultra stable lasers in my lifetime. So we need to build a laser which is going to interrogate the clock. And it cannot be synchrotron and IFL because those are not stable enough or precise enough. So it turns out to be there is one nucleus, just one freak of nature nuclei, thorium-229, which has the low light isomer at 8.3 electron volt, 149 nanometer. Our nuclear physics colleagues initially put it at 3.5 electron volts, which would be perfect. But unfortunately, it's not visible as UV. So the main issue with building nuclear clock, it's not as much the fact that it's a nuclear, it's the fact that the wavelengths is way outside the wavelengths of all the clocks. If therefore it's improved in terms of stability, it's great. In terms of building 149 nanometer laser, it's difficult. So we submitted a proposal a few years ago to European Research Commission, and there it's a very big deal. You actually have to go in front of the committee. There's 15 people sitting on you and 4 of us standing there, and they're like, we looked at your proposal, and it looks like you would like to hire a lot of people to build a lot of lasers. Pretty much this is it. And then we're going to be searching for dark matter. Because there is no CW laser at that frequency. And 5 years ago, no one thought it could be built. Now there's another 5 million grant for people just to build this one laser. So Juni in Gila happened to actually have a frequency come almost exactly where it's supposed to be. They spent a couple of years tuning it to the right frequency, which 2 years ago, no one actually knew what that was exactly. So, and NIST now have at least a prototype nuclear clock. So I'm going to try to, they've done a fantastic video. I'm going to try to play it for you.
In this crystal are atoms of a metal called thorium. And inside those atoms is a secret that could redefine how we measure time. Scientists hope to use that secret to make a new kind of timekeeper known as a nuclear clock. Today's best clocks, atomic clocks, keep time using electrons. These tiny particles form a cloud within the atom. When hit with microwaves or light at just the right frequency, electrons can jump between energy levels. By measuring the frequencies of light that make electrons jump, atomic clocks can count time with extraordinary accuracy. But nuclear clocks could go even further. Instead of electrons, they measure energy shifts inside the nucleus, the dense core at the center of the atom. In one particular type of thorium, thorium-229, a nuclear jump can be triggered by ultraviolet light, which has a frequency much higher than the light used by today's best atomic clocks. That means a nuclear clock could tick more than 2 million billion times per second, making it far more precise than any existing clock. And because the nucleus is naturally shielded from the environment by its electrons, the ticks of a nuclear clock would be exceptionally stable. Nuclear clocks will do more than keep accurate time. Tapping the secrets of nuclear time will help scientists explore the fundamental laws of nature, shed light on some of the universe's deepest mysteries, and open up possibilities in science and technology that we can only dream of today. And inside those atoms...
So the important point, you see this block, and you can wonder why is that at the clock. Well, because we do not have a laser to excite right now a single nuclei, just because we just don't get enough power at the 149. So what people do is they take a crystal, say calcium fluoride 2, and then they embed a microscopic number of thorium nuclei in there. And suddenly atomic physicists now have to collaborate with solid state physicists to tell us what's happening in those crystals. It's actually, so it's very, very hard to make those crystals, and it's also very hard to keep those crystals alive. Because crystals do not like when you shine UV light on them, they become untransparent. They also don't like nuclear decay inside those crystals. Remember, thorium-229 is radioactive, even though it has a very long, thousands of years half-life. So we will eventually be able to actually build a nuclear clock like a traptine clock with a single thorium-3+ traptine. But this is a great opportunity because now we can have actually the only clock only quantum clock with microscopic number of your quantum devices measuring at the same time. So what people would love to do is to use the same crystal which converts light into 149 nanometer, the same crystal where you embed the thorium. And that will require a lot of interesting material science. All right. We also need, obviously, nuclear physics, because now we are dealing with nuclear sensitivities and we are dealing with nuclear computations. So this has been a dream for a very long time. So people knew about this transition for now more than 30 years. So when we wrote our ERC proposal in 2021, the number of digits measuring this frequency was 2. And now we are actually in 2024, people finally were able to laser excite the clock transition. So imagine that's the first time any nuclear have ever been excited by a laser. So they took nuclear ground state, shines a laser, and they saw photons coming out. And very quickly, we got from a gigahertz to kilohertz, and now we actually have precision. As you see, this is the frequency precision, at 12 and now actually 13 significant figures. So progress has been tremendous, so there is no question that we actually will get to super high precision clocks. And that's probably the most ambitious proposal ever to promise that we will improve 12 significant figures in 6 years, which actually happened. So, and for maybe nuclear physics colleagues here, what Gila Lab has actually measured with a crystal grown by our ERC collaborators in Vienna. So the nuclei ground state has spin 5½ the excited state in 3½ So there are actually 5 transitions. So they looked at the nuclear electric quadrupole structure, and again, actually align shapes is the frequency. And they measure every single one of them. So think Nose bias spectroscopy at 13 significant figure inside the crystal, which also parameterizes the electric field inside the crystal, and also measures the ratio of the quadrupole moment for the ground state and the excited state. And the reason why we really want the nuclear clock is, remember the discussion of sensitivity for atoms. In the nuclear, we think that because the energy is a Coulomb energy at the GeV scale, and we think the difference in Coulomb energy is MeV scale, we think the sensitivity to the variation alpha, instead of 0 to 6, will be 10 to the 5. So we think that this nuclear clock would have sensitivity to dark matter 5 orders of magnitude bigger than any other clock. And that's one of the motivations to actually get this clock built, besides the fact it's just so cool to excite a nuclear by a laser. Now, the reason why we want this is because it's just simply easier to measure large effects. So the question was how you can actually measure the sensitivity, maybe determine sensitivity. So I was the closest to nuclear physicist, being a theorist, from the rest of my colleagues. So I got to analyze the experiment, and okay, we assume the nuclei is just some sort of ellipsoid, because that's the only way we can plug experimental numbers and get a Coulomb energy. So they measure the RMS radius, they measure the quadrupole moments, and we plug it in, and we got the sensitivity about 10 to the 4. Of course, the question is, what if the nucleus is octopole deformed, which is probably it. So now we're actually looking for nuclear physics colleagues who can look at the octopole deformation and tell us whether it's bigger or smaller for the isomer. So now, besides the solid state physics, we also look for very, very interesting nuclear physics for the nuclear clock. So, in the last 5 minutes, I will talk about what would we gain by sending those quantum technologies clocks to space. Well, the first thing, if you would like to measure general relativity, the fact that they're actually sitting on the surface of the Earth, it's very unfortunate. Because therefore it's very hard to actually tell normal general relativity from some anomalous effects like anomalous redshift. Also, we would like access to variable gravitational potentials, meaning we would like to first be in a gravitational potential here and then to send the clock either close to the sun or really, really far away from it. Because now, again, we can test GR. Also, we would like to look for gravitational waves in the different wavelength regions. And for that, we need long, long baselines. It's just not possible to do those wavelength ranges on Earth. And for example, on the moon, we have free cryogenics and free vacuum permanently. Therefore, there is a lot of proposals, and I've participated in quite a few of them, and a lot of interest from NASA, ESA, and other space agencies of actually sending the clock to space. For example, if we just take your lab packet, put it on a satellite. That allows to test GR 5 orders of magnitude better than anything you can ever do on Earth. In fact, we already have a microwave clock in space called ACES. It's an ESA mission on the ISS space station, but this is never supposed to be 10 to the minus 18, but it will produce us actual link. And this is why we really want the solid state nuclear clock, because it can be so very compact. If you've ever seen an AMO lab, you can ask how you can possibly send that to space. Well, people already made portable devices. I've seen atomic clock, which is exactly the same clock as in a lab, which fits to about that big. It's still a few hundred kilohertz, and it's also still plugged into the wall. But nevertheless, this is actually not something unreasonable, so we do have technology to actually send those things to space. Some of the more ambitious projects, and this is kind of a ChatGPT variant of sending clocks to the sun. Some of the particle physics theories think that dark matter can actually cluster around the sun, and then they could just simply move it to detect for us. So who actually knows about the Parker Solar Probe mission? It literally touched the sun. So it got to like a few million miles away from the sun. So it did not get destroyed. So it was much closer than Mercury orbit. So the question is, my particle physics colleagues said, okay, let's put your clocks, now 2 clocks in there, and send it to the sun. And I first like, let me just check with Parker Solar Probe people, the clocks won't just die. It looks like they actually have fantastic thermal and magnetic shielding. So it looks like parameters which they actually got in terms of shielding are compatible with the clock technologies. So this is actually one also interesting way to do it. And they think there could be like 10 to the 17 more dark matter particles near the sun in some of the different models. And by the way, being an atomic physicist, I ask a very simple question, like, what if like dark matter just kind of sits as a blob around the sun? How we can tell that? We can't. 10% of the sun could be dark matter and we would not know. So I'm trying to find solar physicists to separate gravitational mass and radiational mass in solar physics codes, and everyone's saying this, you have no idea how complicated that is. So right now there is no limit. If dark matter just sits there gravitating, there is really no limit of how percentage of dark matter would be the sun. And no, by the way, I don't think large percentage of dark matter sits near the sun or in the sun, but it's not excluded by anything. If it's a WIMP or action, yes, we're excluded. If it's just sitting there, we don't know. So we don't know how much dark matter we have inside the Mercury orbit. And the last thing, we would like to probe the entire gravitational wave spectrum, because there is no hope to actually get terrestrial interferometer like LIGO working under about 3 Hertz. You can do actually atom interferometers under 3 Hertz, but because there is seismic activity, those are a terminal problem, which means that we can actually not look at some of the objects from Earth. So there is, of course, ideas for LISA, which is a approved space interferometry project, but again, this is actually in a different wavelength region. So right now, people are actively building atom interferometry devices, which is a prototype gravitational wave detector at Fermilab. It's called Magis 100. They're building a 100-meter vertical quantum atom interferometer, where you could actually separate atomic clouds by very large distances to look for gravitational wave. And now, here between the nanograph and the future LISA, the only idea is to actually put clocks on asteroid and measure asteroid distance to a micron. So clocks at 10 to the minus 18 allow you to measure distances of 1 astronomical unit, 1 micron. Of course, we need to know more about asteroids, and there's been a recent Bennu mission which actually brought samples from the asteroids, actually landed at an asteroid. So this is actually an interesting perspective. So to summarize, in 1926, we solved fundamental physics puzzle of atomic spectra and get the quantum mechanics. Then we got the quantum devices with which we would like to find dark matter. But dark matter is really very fundamental puzzle, but so are atomic spectra. So when we solve those new puzzles of the 21st century, what new technologies would that possibly bring? Thank you for your attention, and I would like to thank our team at the University of Delaware and all of our collaborators.
Okay, it's time for questions.
Yes. I want to come back to the idea of the dark matter surrounding the sun. I mean, you have 17 order of magnitude, I think, that you say there. So, like, what would be the effect of having that amount of dark matter in the sun in terms of the orbit of Mercury?
None. Because dark matter, the reason why dark matter affects the motion of the planets, of the stars around galactic center, is because we have a very, very large sphere of dark matter blob sitting around the galactic disk, and it's a sphere. The density of dark matter in our solar system, it's 1 atom of hydrogen per 3 cubic centimeters. So for the entire mass of Earth, you get a kitten of dark matter. So it's completely indistinguishable from the mass of the sun. So we do know how much mass we can tolerate inside the Mercury orbit from the Mercury precession, and inside, for example, the Earth orbit. And that gives you that mass of the sun is known precisely to about 10 to the minus 10 of the mass of the sun. However, what you don't know, because you see, gravitationally dark matter is not different from the normal matter, but we don't know what percentage of this is normal matter and which is dark.
So what is the mechanism that creates the shell of dark matter surrounding?
Okay, now, that is a very good point. So as of now, my particle physics colleagues cannot produce such a huge shell. They can produce a shell which produces overdensity by several orders of magnitude, but not 17. So the one way to do it is just simply gravitationally. Okay, you have gravitational object and dark matter kind of permeates and attracted more. This is not enough. So you can do it through self-interactions of dark matter within the allowable limits. So there are mechanisms, people are working on how to get those type of objects. But again, this is a theory.
That's also assuming that the same unknown dark matter that is outside the galaxy that is surrounding the sun.
Right, right. But the mass of the sun in any stars is so insignificant compared to mass of the dark matter that you can add another, like literally another luminous galaxy to the Milky Way, and it would not showing up much. Because remember, our dark matter density is known to only 50% from the experimental. And by the way, we have no idea how much dark matter we actually have in the solar system. Despite the fact we're all plugging in at the same number, there is no experiment which tells you that's how much dark matter we have in the solar system. We actually had a paper about it. We used this asteroid Bennu orbit to look at the precession of the orbit to see if we can place limits on that, and we're like 5 orders of magnitude away from this 3 GeV per centimeter. So the orbits are just not precise enough. And they're not going to be precise enough because they all tested from Earth, and Earth actually core wobbles a little bit to about a few centimeters. So you cannot determine precisely orbits from Earth. Yes?
May I ask, is there any result that prove this kind of method work? I mean, do we have the results prove the dark matter or dark matter field really exists?
Okay, so the reason why we think dark matter exists is because we see effects of unknown mass at every astrophysical scale, at the scale of a galaxy. Now, whether ultralight dark matter exists is a whole different question. However, a lot of dark matter theories, a lot of particle physics theories which have nothing to do with dark matter naturally produce ultralight scalar fields. For example, you have your string theory, and you would like to compactify the 4-dimension. You start producing some sort of ultralight, some sort of modular fields which could have dilatonic complex lenses. So there are reasons to introduce ultralight fields in particle physics, which also could be dark matter. But yes, it is a theory. We don't know if it exists or not.
But Professor, my problem is there any result to prove?
Well, we are looking for it. But so is the rest of the particle physics. Been looking for the dark matter for the past 50 years. And we all assume that dark matter interacts with us besides gravity. This is actually not known.
So Professor, this may be a little bit offensive, but this experiment seems like 100 years ago, scientists trying to find ether.
That is a very interesting question. And I can tell you a more interesting question. Do you believe that Lorentz violation holds? And we don't know. So the best limits on Lorentz violation actually for electrons actually done with clocks. So my answer to you is that our modern physics are based on postulates which we just said so. We said so that Lorentz violation holds, period. We believe equivalence principle. We have to test it because our devices are working at a level that, frankly, we really have to check whether my clock here works the same as a clock in Japan. Because we don't know of position invariance. It have not been tested at that level. So those devices are that precise. So besides searching for dark matter, we're also building devices. By the way, the clocks are, those super precise clocks are going to use for geodesy and many, many other applied reasons. That's not the only reason they built it. But they also can look for dark matter. So think about, instead of building a collider, which is dedicated for dark matter, like you can produce, presumably, those particles at LHC. And by the way, this is also a great device. This is a whole different question. But in my case, those devices are built for completely different reasons, and they can also look for dark matter. So, and also, precision field. When people discover dark energy, they were not looking for dark energy. They were looking to measure expansion rate of the universe, and they stumbled upon it. So, for example, we are also building from the same device as quantum computers. Does quantum mechanics works in large-scale systems? We don't know, but building quantum computers will tell us. So this is literally looking for the completely unknown everywhere where we are. And there is also good particle physics theory reason to look for that.
Okay, last question.
Students, especially sitting in the back.
No
or in the
questions?
sides.
I have.
Like,
Yeah. I have two. So you said that for the atomic clock, it has the precision to see height difference in 1 millimeter, right?
Yes.
What is the mechanism? Is it sensing the difference in gravitational potential?
Yes, it's just difference in gravitational potential. So what they do, it's literally it's just basic general relativity. The tick of the clock depends on the height. It's the fact that it also depends if the clock is moving. So, but the way it's done is actually interesting. So, as you see, those atoms are trapped by light. So they trap light, they make this trap very large. They literally trap atoms, so they have atoms throughout 1 millimeter. And they literally make part of the atoms work in the top clock and part in the bottom clock. And they can measure the clock differences between the top of the trap and the bottom of the trap.
So following that, is the nuclear clock also sensitive to that?
Any clock is sensitive to changes in the height, because it's just general relativity that frequency, which tick of any clock, is dependent on gravitational potential. Right?
So then, if you have the light dark matter, but they also have gravitational potential, because you assume that they might also have some mass.
It looks different. So the way, like, you're asking a very good question. How do we distinguish dark matter from, say, Lorentz invariance violation or from anomalous redshift? They manifest themselves differently. So for dark matter, what I do, I measure the ratio of clock frequencies over time. I decided to be a bit too technical, so I didn't go over that. And then you have this time domain measurements. You convert it, you do Fourier transform, you convert it to frequency domain, In the frequency domain, you should see one clear peak at dark matter Compton frequency. So this is a very verifiable signal. For Lorentz invariance, we actually are looking for different things. We look to identical clocks with magnetic fields oriented differently. And then we look for sidereal variation with Earth rotation or with the Sun rotation. This is a very different sinusoidal. For the general relativity redshift, we actually are looking literally at the just drift with gravitational potential and shift. So, and therefore, it's possible to decouple these effects. But if you see the signal and if you're certain that's a signal, you're not. I mean, you found a new particle, which is ultralight. So whether it's a dark matter, that's a whole different question, by the way, which is also very interesting. So, but yes, there could be multiple new physics affecting clocks. And for now, we sort of think we know how to distinguish between them because we look at the different experimental signatures.
So I might be thinking this wrong, but you say that dark matter behaves like wave. But what if it's like the wave goes in every direction and then the phases and the oscillation all gets canceled out?
So
one way to
yeah. So look, you have a scalar field. The simple solution, like if you write a particle physics equation, which has for a scalar field, the simplest solution is a plane wave. Therefore, at the first order, it is a plane wave. So unless you're writing some more complicated theory of dark matter, but if it's just a scalar particle, it's just a cosine wave. However, dark matter was called virially supported. It doesn't condense, meaning that they're moving in random directions everywhere. So the concept of coherence there is quite interesting. So you have some sort of a coherent blob, which is sort of within this blob, dark matter can be considered coherent just because it's within the de Broglie wavelengths. You are not necessarily the maximum of amplitude for that wave, therefore you just measure for several de Broglie volumes to get your full result. So, by the way, axioms also have to do exactly the same thing, and they usually don't bother. So you have to be within a few coherence volumes for axioms as well. Zero Butker and others wrote a paper about it. So all of this is more complicated, but plain like cosine omega t has to be there if it's ultralight dark matter. So you can't go away with that. Now, if you have violation of Lorentz invariance, that you could have directionally dependent field, but then interesting things happen. That's a whole different question from dark matter. So,
right. Thank you.
Okay, let's thank our speaker again.